Number 2, draw the Lewis structure and use the Vesper theory to predict the molecular geometry of the following molecules. So we're starting with SO2. Okay, the least electronegative atom there is sulfur. Okay, so it's going to be in the middle. Let's see, we got oxygen on either side. We're going to have, goodness here, the best that it can do would be a double bond on one side and a single bond on the other side. The best you can do, we'd probably have a resonance structure here. And that's all well and good. Resonance structures aside, which side am I supposed to put this double bond on? That's not actually any of our concern right now, because when we're trying to predict the molecular geometry of the following model, what's important for us to know is that sulfur, that central atom, is going to have a lone pair of electrons on it. And regardless of how many bonds are coming out of each side, regardless of how many lone pairs these oxygens have, regardless of which oxygen has a double bond, the fact that there is this lone pair of electrons right there is going to add repulsion force to all of these bonds, pushing them down from the lone pair. And so they're going to be coming out at this orientation, making it bent. I know that because of this lone pair of electrons right here. All right, Ci4. Okay, Ci4. So we have carbon and iodine. Carbon's there, so it's definitely going to be my central atom. I'm going to surround that carbon with iodines and then go to town on my valence electrons. Now, you might have confused that I for an L. You might think this is just 4 chlorine atoms. That should make you a little bit suspicious, because 4 chlorine atoms is just a mass of chlorine. That's a whole bunch of nonmetals together. Also, there are slight differences in the fonts that depict lowercase L's and capital I's. And if you're ever not sure, just ask me. You can just ask a question. It's as simple as that. We have to be able to do that. All right, so we have the exact same dipole moment in 4 different directions. Okay, we have the exact same dipole moment in opposite directions. So what that means is each of these dipoles is going to be canceled out. So this is going to be a nonpolar molecule. You don't have to write that down, just pointing that out. But the central atom surrounded by 4 atoms is going to make this tetrahedral. And C, looking at BCl3. So the least electronegative atom there is the boron. I'm going to surround that with my chlorines. Just on a side note, when you guys get to a point where it's annoying to write in these valence electrons, because that's what takes most of the time in drawing these structures, that's when you know that you've made it in terms of understanding Lewis structures. All right, now to identify what type of shape this is, first off, we know that it's trigonal, however we want to say it. We know it's trigonal because there are 3 points around this central atom. The question is it trigonal planar, meaning is this a completely flat molecule, or is it trigonal pyramidal? Does this form a small pyramid? Now, in order to answer this question, I want to refer back to A. The reason that we knew that this was bent, the reason that we knew that these 2 bonds coming off the sulfur were going to go down at angles is the presence of this lone pair right here. The presence of that lone pair is forcing these bonds to move and be at angles. Here on boron, because boron only has 3 valence electrons, it makes 3 bonds, but then has no more lone pairs. There are no lone pairs around this boron atom here. And so there's nothing to push either or say any of these three bonds here at any angle except for with respect to themselves, like that 120 degrees from each other. There's no lone pairs present to push this in or out of the paper, okay, using that z-axis. There's no lone pairs to push that. So this is going to be flat. Trigonal planar. Now, if for some reason this boron did have a lone pair, for example, if this was NH3, okay, and we'd make this structure, and we see that there's a lone pair, yeah, this lone pair is going to push these three down in three-dimensional space to create a trigonal pyramidal, but again, that's not what we see because we don't have that lone pair on the central atom.